So, thank you for introduction. Dear colleagues, ladies and gentlemen, I would like to start and I would like to introduce you the method which I believe that will replace all the other methods for connection design. And I would like to appoint in my presentation three questions. I would like briefly summarize where we are in connection design, but it will take time. I would like to go a bit to detail. And then I would like to have a look on the what finite element procedures we have are available for connection. And then I would like stress the importance of validation and verification, because this is the, if we do discrete models, if we go for finite elements, we have to be sure that the procedure is going to proper results, and it's not so difficult, but it's there is already developed system. So to go to these goals, I would like to have three part of my presentation. The first part is connection design. So history, let's say. The second part is validation and verification, also from, let's say, a bit university point of view, a bit academics, a bit theory. But I have the second hobby. I do fire design and fire. We have also a branch. We are teaching at our university fire specialist, and in fire modeling, it's really well established, this validation verification. So actually, I learned it not in finite element classically, but I learned it with models for finite elements for fire. And we publish also 2 books about the validation and verification in fire engineering. So this is the second part. And the third part, I would like to go to component-based finite element, where we are working on it already for 10 years, but we have intensive project for last 3 years. But of course, I will not be able to show too much. So I will focus only to, let's say, two questions from all this to show you where we are, and these are, let's say, separate, but so slender plates, and I think we have a relatively good solution already. And the second is Wald's behavior, and on this part I'm on the other hand very surprised, and that we are working, it works very well, and it's due to the fact that I have a good colleagues, and we are happy to have a good students. So to go to summary, please interrupt me if it will be too boring, or if I will be repeating what you know for a long time and what you are using every day. So if we have a connection in the structure, we have its flexibility. And if it's deformed by normal force or by rotation, it has basically no influence to distribution of forces. And also, like in shear force, if you erect the structure, it locks. So there is no, if there is a gap, only in some extreme, in some earthquake design, we may have a difficulties. What we see sometimes in connection with experiment, that there is some slippage. that it does not exist on structure because by that that load, by its load, its weight, it's locked. On the other hand, the bending stiffness is known from 1917 by experiments in US, and 1930 the first standard in Britain. So the bending stiffness has an influence on the force distribution, and it goes, of course, as you know, to extremes. If we have a column base, basically it's rigid, but it may not be rigid, and the engineers, we are playing with the game to make it simpler and to be able to design it. So the connections from this bending point of view are designed for bending moment. And so this is traditional design for bending moment. But with informatics and with full description, we are going also for stiffness, and we have initial stiffness, which is completely different from the safety point of view, because it's only initiate the distribution of forces, and it's like modulus of elasticity for material, and so we do not need really so much accuracy, and we do not need to have a safety on it. And then this deformation capacity. The deformation capacity, I would like to go a bit further. So as we have a experiment, we are not going to reproduce the experiment. We are going like with elements to our engineering good procedure. We are going for yielding of the material, and of course it's not true, but it's a very good engineering judgment, and our design is based for elements, steel elements, on this model, and we are using this model, or it was previously used also by our grandfathers for connections. Of course, there are some more complex things that for bolts, for welds, we are taking really the resistance. And this was also the reason that I recognize that for just finite elements simulation without taking special care of connectors and this and special part is impossible. So deformation capacity or rotation capacity, if I'm going for connection in bending, it's special. It's really a question of safety of the connection, because we are afraid of brittle, even if we are designing for not seismic, not dynamic. It's related also to robustness of the structure. And if we are going for plastic design, it's crucial. So rotation capacity is also sensitive to level of design. If we are very low, the deformation capacity may be more. And the plastic deformation capacity, it is deformation capacity. The elastic part here is a bit out of scale. The elastic part is not of importance. So historically, the engineers, the good engineering judgment was used. So we have till now in Eurocode, we have brittle element, we have ductile elements, and so this is the procedure as we have till now. And of course, we are trying to avoid brittle fracture, shearing of the bolt. We are trying to have a bearing of the bolt. And it's very known, and this is also one of the reasons that we are using this engineering good, deemed to satisfactory ideas, because actual yield strength, it's unknown. For areas where it's not necessary, we do not need to know the upper values of material properties. And as all the steel people know the lower value is really lower and seldom delivered the value which is the lower value from a steel producer, from steel mills, and it may be rather higher. And so it may happen that if I have a brittle component, brittle part of the connection, and I have ductile component, and if due to this material upper values, it may change for me, and then I may have a brittle connection. It's like ductile is plate in bending, brittle is bolt, so it may easily be the bolt changed to bolt fracture, or and so this is all the time. Of course, especially for seismic design, it's in Eurocode 8, part 6.2, chapter 6.2. 6 is for steel structures, and 6.2, it's 2 pages questions how to solve it, because for dissipation of energy is crucial, of course. So, but also in connection design, we are faced to this. So. So this was the introduction. This was, I was trying to appoint some important questions from connection behavior, and now I would like to summarize briefly. I hope that I will catch the proper, maybe it's proper level, because maybe it's completely not necessary. Maybe it's good to summarize it, and as I have here the space to go for our new method, I have to start where we are. So we have Eurocodes, we have a special chapter, a special volume, we have a special part for Eurocode design, and connections are not only in this, they are also once more in bridges, specialties. They are also in these parts where the different structures are mentioned, but also connections for composite structure are in composite connection in composite, and of course connections are also in your code for seismic seismic behavior. So, sorry, and models. So, what models are available now in this in this field? So, from beginning of steel structures, the experiments were important. They were used. Then we have curve fitting models. This is some generalization of experiments. We have analytical model. That means equations. They fit physical behavior. They are describing physical behavior. And we have discrete models. We have finite element analysis. And now the top, as we call it in Europe, the top procedure of analytical model is a component method, and for finite element we have research model, and we were trying, or we are preparing, or for 10 years we are preparing this design procedure, and now we call it components-based finite element method. So physical experiments are very simple. We have databases of experiments. It was, let's say, 80s and 90s, where the experiments were summarized. Maybe you know that till 95, the dust tables, the German tables, they are used around the world. At least they are used they were used in Czech as well, or we have our modification of this, but they were fully used based on experiments. till the 1995, the engineers, they were not really reproduced by analytical models, the experiment. So they are from this 90s, there are books, American books, Shen, Wi-Fi Shen, and so it's a book where you have 6,000 experiments. All are well described, of course, all the time some information is missing. So then there are some, if you calculate by component method, you may create some curves, and then is this curve fitting, classical curve fitting is not used, but it was developed in 1917. But the first publication about this procedure, if you have an experiment, you may, based on some parameters, it's easy to do it for top and seat angle connection. That and it works. But as you understand, it's not appointing, especially the resistance. This model is still used for seismic design, for seismic modeling of if you would like to have a behavior of your connection with unloading, and there are some famous models for this. But so this is, and of course, I think you know the surrogate models. Surrogate models are popular in many branches. They came actually from movie, from doing the video or or virtual reality, because and there are famous studies. This is the SUMO project from Delft University, and this is from this film. This is from one Czech poster for some movie, and how the human body is modeled. And the trick is that you have a lot of simulations, and based on the simulations you have some models, and then you put mathematics, you apply mathematics, you apply some functions, but they are not simple. It's computer oriented interpolation, which allow you also to play with the accuracy, with the probability, and finally the lady, the body is moving just continuously, just from few calculations, because you are not able to model it in real time, but you are able to use the function in real time. So this is the trick. Now it's also used in connection design for hollow section. Our colleagues in Finland, they've used these surrogate models but I do not really think that is the future, because you should have a pre-calculated models, and we are engineers, we are trying to have all the time something new and with what was not here not before, and even in connection design. So the surrogate model may do only what you calculate already by some advanced model. And second area are the hollow section. You know that the hollow sections are designed by SIDEC models. The SIDEC Association of Producer of Tubes, they prepare models for resistance. It's for offshore structure. Basically, it's driven by offshore industry, and many European universities are working on these projects. But it's mixture of curve fitting and analytical procedures, and the trick is that they describe the failure mode. It's 7 basic failure modes in this material, and so this is I have here failure mode A, which is the most easy to describe. Plastic failure of hot phase. So this is, but it's not described really by analytical model. It's described based on experiments, so it's going a bit higher than a simple analytical model. But all these models are very limited in the geometry. So firstly, it's only for class 1, class 2 sections, for not for class 3. And secondly, the geometry is limited to knowledge to test, available test. And so here I have the 7 rest failure modes. Each is different. Some are very complex, some are simple. Very simple is this shearing or shear failure of the rod, because we know very well of shear behavior of beams and elements, so including buckling. But here is it's treated a bit different way based on experiments and on some factors. So this is this possible failure mode. Maybe you know that it's already 5 years project. SciDec. No, not yet. So this material, SciDec, is in the chapter 7 of Eurocode 8, summarized, but it's old-fashioned. Now they have, I think, the 5th generation of this equations of this knowledge, and the last generation is in ISO standard. The World Welding Association, they were interested to have it as a ISO standard, as the whole standard, whole world standard, and so the latest version is in ISO 14346, and just last week, the ECCS TC10 for joints, so technical committee of Steel Fabricator Association, which is taking care of Eurocode 8, decided that in the 3 years period of the transition to new generation of Eurocodes will be the chapter 7 not published in Eurocode. It will be this ISO material will be transferred to EN ISO to have it Europeans to have it under control, and it will be used this way. So how this? What is in this chapter 7 or in this ISO material? So they are for circular, square, and rectangular hollow sections. They are described, these 7 failure modes, for one plane connections and multiplanar connections. For beam, for hollow section, 2 open section connections, which are also popular. There is the model is only in plane, uniplanar plane. So this is available. The procedure, maybe you are using it every day, so I'm a bit handicapped. Maybe you see the first time, but the procedure how to come to equations is that the joints are classified based on geometry, K joy, KT, N, and so on. And for some geometry, for limited geometry, it are available this, let's say, 7 equations. And to simplify it a bit, for more complex joints and for this more plane, is also available a lot of knowledge in this SciDec material, and it's summarized in these complex joints. So the tables looks like this. The trick is that in this table, if you have a, let's say here you have a failure mode, for hard shear failure, the most simple failure, and then you have rectangular, circular, and or open to hollow section, hollow to open sections. Then you have a list of, based on geometry, you have list of failures which you have to check. Of course, some are not logical, some may not occur, and some are recognized that they are not crucial, critical. So this is the basis of the SIDEC material. Here I have another brace failure. So for rectangular, circular, and chord failure, based on the geometry K, you have tables with these equations. 5 years, I think already 5 years, the SIDEC recognized that it, in some countries, I don't know really in Belgium, we discussed it last week in this committee, but in some countries very unpopular, this Annex 7, because it's rather unclear, and it's based on K factors, that you calculate some factors and you do not know. I'm from Czech Republic, so at the Czech engineers, they do not like it too much. In the previous, we were using some Russian models for this hollow section, and so SIDEC, I think with big support of British part of SIDEC, Tata, they asked to build a component-based procedure. There is a 7 failure mode, so it's known from beginning that it's possible. So there is like 7 components in this connection, and Professor Jaspar from Liège and Klaus Weinand from Aachen, they worked already for 5 years on this project, maybe only 3 years. It was pre-discussion, and they deliver already these models, I think. And so they transfer simply the same equation, the same knowledge, but really different philosophy. I really like this philosophy, because it's engineering friendly. You understand what you are calculating, you understand what is the lever arm, you understand what is the failure mode, you understand what is the effective width. So instead of these factors, you have an effective width. You calculate what part of the joint is taken into account. So this is the procedure which will come, and it looks like SIDEC is very motivated that it will be in 3 years, it will be in the Eurocode for connections. So this is where we are in hollow section joint design. And for open section, I think you are very familiar. This is the component procedure. It is not completely revolution that we have equations for stiffness, which are engineers are trying to avoid the calculation of stiffness, of course, and we have some summary for how to calculate deformation capacity. And resistance is calculated based on the good engineering judgment inside the connection, what is the lever arm, and distribution of normal forces or forces, just force, to each component. So the component method is relatively easy if you have a good judgment of your lever arm, and it's unbelievably accurate. As I did the connection tests in US and in Prague and in Japan, all the time I was surprised how accurate it is. even for stiffness, for resistance, but of course never for deformation capacity. And so I have here example, but there are plenty, thousands, let's say. And this is a bit complex, so it's this joint beam to column end plate connection with 6 bolts in 3 bolt row, and it's loaded by Mn interaction, normal force and moment. And we are using linear interaction, or we may calculate by component method. And here I have a result of the test, and here you see how accurate is even the prediction of stiffness. And the resistance, of course, it's very different to ultimate resistance, because it is the resistance that we would like. We would like to have a based on yielding, based on Fy, based on yielding. So you see, this is we load it, unload it, and then we predict it, and it's completely it fits. And so the component models are very nice. They are a bit too accurate for design, but you may model only what you have the knowledge. There are basic components are in standard, few components are also out of standard in some literature, but you should be able to do the calculation of the you should be able to do the prediction of the lever arm, and this is not all the time so easy. So now the books about the standardized connections, the experiments were replaced, let's say 95, the blue book, and a bit earlier, I think already 87, the green book, the British Steel Institute book. And there is a lot of computer programs. I think you know it, you are using it. This is one Czech one, but all softwares, they are focused on steel structures. They have a nice component-based method. RFEM has a beautiful, very complex tool. And you have inputs, but you should have a connection which fits to your input, of course. You have output, and you have a nice report and the full description. It's for beam to column, for any connections which are standardized, let's say. Also for column bases we have, and I have had the opportunity to prepare this material, background material for column bases. So I think it works very well. And it's here I have the model. This is for base plate. If we stiffener, so it's reproduce the behavior. The prediction is in different stages. Is very well. So there is a lot of references, a lot of literature for connection behavior. The basic, the oldest, the traditional literature is Agerskov from Denmark, Professor Agerskov. I do PhD with him, and then Zutemeyer, Dr. Zutemeyer. He published like Bible. He published the knowledge which he reached in Delft at VTT before it was Stern Laboratory. And then next step, like next generation, was work Professor Jaspar on beam to column connection, and also other colleagues. And I have had the opportunity to prepare this column basis, and then I think some summary and generalization of this component procedure was published by Professor da Silva. And this special question of deformation capacity, I think, was summarized in many papers, but also, but my favorite is the Professor Beck on rotation capacity of moment connections. So this is the, let's say, in a review. And now I'm still in this first part, in this introduction, and what is available for finite element analysis. So, as I mentioned, we may classify the research-oriented and design-oriented finite elements. To be honest, till now, in research community, it's expected that there is no chance to design for design model by finite element due to big specialty in connection design. And it's true that it's complex. It's true that it's different. And so there are like research-oriented models, and there is a history of this. And now, let's say, last few years, are coming the design models from by finite elements. But because it's the time, the modeling is getting, the tools are very strong, the computers are just able to calculate these questions. And so if we have a look on this research models, so now there are unbelievable models of bolting, even even the tightening the nut. I saw the programs, they are taking care of the tightening of the nut to model the history of stresses in all the connection, but to be able to simulate if you tighten this corner first and second corner later, or you retighten it. So they are really very nice models. For bolts, also the colleagues, they came, we leave already the plastic criteria. We went like concrete people to the damage models. You know that they have difficulties, these damage models. So this is the bolt itself. It's modeled by 3D elements, and it is very research oriented. To be honest, this on the right is this is a rather simple procedure for this model. And then we are coming, let's say, to simplify design procedure. One is contact model. There are more publications related to matrix, which deformation matrix, where you merge some points and you create environment. You create some bolt assembly and bolt behavior. And the second traditional solution is fun model. The fun model has advantage of the simplicity and of the more engineering way to be described. So we are using basically the fun model, and because it's also the oldest design solution. And now the last in the bolt, of course, it's not only bolt, but it's bearing of the material. So research models are now very complex, mostly based on yield criteria. On not for damage models are very seldom used for this basic material, or what I saw. and these models are in Europe. I think the Ljubljana, what I have here, model, and also at Delft University they develop very special models for bearing. Nowadays everybody are working with high strength steel, so for different steel or for stainless steel, or this is and now the history. So the oldest published complex model of connections is from 78. It was 2D model. All the time the researchers, they use this model with experiments. I think it's necessary to see the behavior to be able to model it. It's not a good idea to have it from database. And or what this is what we are using doing. This is what we are thinking that it's necessary. So then they come another generation of models after, let's say, 10 years, as I am studying this and I am working in this. And surprisingly, this is, let's say, the first model which the colleagues, they were already American model, but they were already thinking how to use it, how to make the bolts. So this was, let's say, first component approach for this solution by Bahari. So then came a big study by Bursi and Jaspar. They published 3 famous papers, and they start to model T-stub, and they were also simplify to be able to calculate it. It was mostly 2D model, and so this is this model. Then they came more advanced models and more research oriented models. I have it here. I do not have maybe enough nice paper, nice figures. Basically, each authors, they studied a bit similar. Here it was model of the stiffeners and bolts and stiffeners, bolts in corner. And some models, they solve very particular questions, like here the finger shrimps, which is attractive, important, and which was never before. We were, of course, it's difficult to measure on the stresses. You may put there only in experiment carbon paper, but that's all. And so it's they are very nice works on this. And it develops in that time. The ANSYS was the leading code. So all the time, all the models, they were made in ANSYS, and now Abacus is more popular due to price at university. So now the models are more to in Abacus code prepared, including the damage characteristics of steel. So this is, let's say, the summary of the research which is available in finite elements, in the connections, in the connection models. So is it clear enough? It's not, the introduction was rather long, so I hope it was not, it was okay. Are there some questions? May I, what was missing? And from your experience, I expect that you are designing connections every day, so maybe the summary was too long and say nothing new. So hopefully I will switch to validation and verification. Maybe there will be some new material for you. So validation and verification is from beginning of finite elements is a crucial question, and it's well worked, it's well prepared, and it's also standardized. So leading, of course, is US, and in US there are different standards, like all the US public bodies, they have their standard for advanced models for finite elements. And so you may find the guides for soil mechanics. You may find guides for nuclear power station. You may find guides for validation and verification for airplane industry, and you may find guides for dynamic simulation for towers. So it is very, and to summarize this briefly, validation is to compare your model against the experiment. And verification is to compare your model against another model, which looks nonsense, which looks stupid, which looks, compare model to model has nothing to do with reality. But it has a sense, and I would like to explain you. So validation is the top, is the most important, and is the cream. But it's not so easy to validate any model against experiment. So there is some internal step to this verification, and I was trying to explain it. This is from fire engineering. Actually, the graph is from fire engineering. So if you have a reality, if you have a fire, and you are trying to have a computer model, you have this is the terminology of firemen, and so you do some conceptual design, conceptual model, which is not really representing the accuracy, the reality, but it's help, it's simplification. In fire engineering is maybe nominal standard fire curve, or it may be zone model, which is very simple two differential equation description of area of energy in fire and in room. So then validation is between the reality and computer model, and verification is between another model, simple model, or more complex model to asked model. And in air industry, it's described a bit differently. So if we have a reality, and then we have a computer model, but it's basically almost the same, and we have some mathematical expression of this reality, we may verify the model to know that it works well on some simplified concept, and we have to validate the model on experiments, but reality is something different. Of course, experiment is also only model of the reality. So this is the story. Maybe you know from this informatics, there are two most famous stories. One is this shutdown of American fighter, F-22 Raptor, because of crossing the date line, and it was really, but the pilot catapulted. But so it is very famous. Just by simple back, everything stopped, and the pilot was happy to survive. So, and so this is this is most from our area. This is the most famous disaster due to the simple pushing another bottom. They calculate this platform, the concrete concrete part of the platform. The cells they calculate by linear calculation, and also they a bit under design the walls, and finally cracks occur as they sunk it everywhere, and they lost the platform. Unfortunately, they already instrumented it, so it was really it is the most famous disaster due to the not proper use of validation and verification. And but to come a bit to our area, you know that the most advanced knowledge is in electronics, and they have the majority of publications about validation and validation. Not surprisingly, engineering, civil engineering is in a very good position, so we have very good knowledge. Of course, there are some models, like weather prediction or economics, they have a very weak, very weak difficulties. If we have a look on civil engineering, we have just linear static analysis. This is for elements. We have dynamic analysis. We have some crash test, transient calculations. And if we merge, this is what we are doing in fire engineering, if we are merging CDF calculation with structural fire with structure behavior, with transfer of heat and fire behavior and structure behavior, these three. So it's a bit complex for validation and verification. So this is very important is hierarchy. To validate step by step or to verify step by step, not to start, but it's very logical, not to start from all the structure. Yeah, it's better to start from material, to be sure, from connection, from for subsystem, for elements, and to go to all the structure. So it's obvious, but it's good to mention it. For this theory of validation and verification is some system response quality, it's called. The system response quality, if they design the airplane, they establish the system response quality. That means what should be validated, what should be only verified, and how to reach the high quality of model. And we built also system response quality. I will show you for our model, but it's a bit more simpler. It's not so so advanced. And also in this validation business, it's not completely necessary to validate on this what you are modeling. You may validate the model a bit differently. So application domain is not necessary to be validation the same as validation domain. It's not necessary to be subpart of validation. They may have a common parts, but they may be also a bit different. This is what we are also using, but it's a bit tricky, and it's we have to take care of this if we validate and then we calculate something else. So this is, and also it's very known the matrix to how to present and how to calculate this procedure. How to present, especially if we are going to probability studies, it's getting, let's say, the third dimension to be there. What is also known is that the models, they do not need necessarily to have a high accuracy locally, but we are looking in this validation and verification on global behavior. So we should appoint what is important and what is not important. So sometimes we do the test and later we calculate, we validate the model, and based on the model we are observing what we cannot measure. So it's good, but global behavior may be the same, but local behavior may not necessarily be fully correct. And of course, very crucial is meshing. There is a procedure, very clear procedure. There are at least 3 methods how to check your quality of your meshing. I think maybe in Belgium you studied more finite elements than in Czech Republic, so maybe you are aware of these methods, but I will summarize it briefly. The simple one is that you do some analytical equation, some just analytical model, and then you calculate it by finite element, and then you know what is correct value, and so you select the number of or your discretization, your elements on the proper size. There are full studies, you know that there are softwares, they are automatically changing meshes, and so there are doctor theses, there are books about this theory of meshes. And the second, to simplify the procedure, you take very rough mesh, you take very fine mesh, and you use some function, it may be even linear function, and you take what you would like. So these are, let's say, 2 very, very simplified, these thick books and very nice papers, very nice work. I have here this assumption solution, so it's not linear, it's Richardson extrapolation, so it's called grid convergence index that you calculate based on the three assumptions. You calculate your grid size. So this is the most popular and the most acceptable solution how to reach some accuracy. And if we have a look on the probability, if we have some simulated item and some actual item, and we have the probability which is a bit far from our from the reality, it may have happened that we got the very good result, and if we improve this already, let's say, good result or not enough good result, and we shift just the results, it is a danger. So this is called calibration, and it is danger word in business of finite elements. Calibration is not good. On the other hand, we calibrate very often, especially if you are if you are using damage model, maybe you know it. Each of these damage models, they have some functions, and you have 7 parameters. You are asked based on your material to calibrate the 7 functions. But then it's very difficult to judge if it will work, if you will use it for some different purpose. But for your material, it may be correct. So this is example of calibration, which is not in steel. In steel we have everything so simple, so we do not need to calibrate. But in many branches, for us it's a bit difficult for steel people to understand that there are people, they calibrate their model. We are never calibrating. We are just taking steel because our material is very simple. But it's not only in material, it's also in another parts of the modeling. And now about benchmark problems, benchmark cases. So benchmarks, I think you know it. Benchmarks are worked example where you have very nice described input and simplified input, and very nice described output and simplified output. And benchmarks are made not really to compete the softwares, but they are mostly made to teach the proper application of software. And they are made to ensure the users that they do it well, they do it properly, and if they calculate the benchmark, then they go to their own some special problem. So we like at universities benchmarks. We have at our university benchmarks for many many parts, especially we have 2 pages, web pages for fire engineering benchmark. But there is an official Wald institution driven by Americans, which summarize the benchmarks, about 300 famous benchmarks they have. This year they have a plenary meeting in Europe, and Professor Franzen from Liège was presenting the fire questions. So this is, and in fire engineering we have standard, ISO standard, and we have different countries, they have their standard to check the quality of calculation by benchmarking. And in connection modeling, if I go to connection, in 97, Bourset and Jaspar, they published this T-stub model. This was like benchmark. Later in 99, most universities, we also calculated, but the winner were we calculated their experiment, and but the winner was from Clermont-Ferrand, the colleagues from Clermont-Ferrand. So this was so in the connection design, but it was in the field of research-oriented connection design. So where we are, so this is our hierarchy, this is our system, where how we are trying to approve our model against the experiments, and how we are trying to verify it against Eurocode, because Eurocode is summarizing the good, best engineering practice from steel engineers from all the history of steel structures. And so we have welded joints in shear, in bending, long joints where you have stresses at the end of the joints, and welding to flexible plate. We have bolted joints, bolted connections, so we have T-stub in tension, splices in shear, and we would like to have some generally loaded connection. And we have slender plates, so it's haunch, it's stiffener, slender plates in compression. Of course, in connection is not so good idea to have thin plates. And we have row section connections, and we have column bases. So we have also some verification, and we have some procedure. We establish how the benchmark should look like, how this verification should look like, and it is finished with benchmark cases. And I forgot to mention that now at the end of my presentation, I will try to show you the T-stub intention and hunch, what we have. We have more, we are working on all. We have 6 PhD students doing their thesis in this subject. And but I would like, I will be able to show you only these examples. So, component-based finite element model, we have to have a look first on the material, then we have to have a look on different connectors, bolts, welds, anchor bolts, and we have there the question of slender plate, and also we are modeling the concrete block. To simplify it, we are using, instead of concrete block, we are using elastic or Winkler hemisphere, elastic hemisphere. So this is the, so material. We are not going for true stress, true strain. We are not going for resistance. We are calculating plastic yield strength. We have advantage that advanced models in Eurocode are summarized in chapter it's chapter 3 and annex C in Eurocode 5. So there is a recommendation that for design purpose we are asked to check the 5% strain. So it is like safe, because you know that steel should have a 15% strain, and we are and for design we are using for plates 5% strain. So instead of bricks, for design model we are using shells, and but we are using relatively higher level of freedom. So we are using rectangular 4 nodes to allow plastification, to allow membrane effect, and to be able from the same element to calculate the bifurcation of the, to check the stability. So this is the material and representation of the material in our finite element model. And secondly, I am coming to slender plates. And so if we have a look on this, we have a connection, if moment connection. We have, if we have a stiffener here, we may separate the stiffener as a triangular plate. And then we do some research model by, we use RFEM for this model. We implement geometrical imperfections, we implement geometrical material properties, nonlinear, and we are able to calculate buckling analysis. So we have this model. First, we validate this model against experiments. In literature, there are 2 sources, actually 2 PhD theses for slender plates of this type. With stiffener, but we did the 3rd study like, and we take also care of the partial stiffener. We have a free edge, partial stiffened edge, and fully stiffened edge. And I hope you see it a bit, but basically we do test of this, we do 9 tests. We were happy with 6 tests. The 3 tests for full stiffener, we have difficulties to break it. We broke it, but we do not have a full data, because we need to change the jacks to finally to broke it. So we have results, but not very nice curves. And so here you see some figures from the experiments, and finally I would like to show you the attractive where we are. This is our validation. So this is the experimental result. This is what we are able to calculate with RFEM research-oriented model. We were happy with this. We were not really going to too much to go more advanced and more advanced models. There were some ideas of my colleague. She is in charge of this. She is her PhD, but we were happy with this. And finally, you see the resistance if I compare experiments to finite elements, to advanced finite element model. And the procedure is to first we do buckling analysis, and secondly we took fully Annex B from Eurocode 5, and maybe you are aware, maybe you are using it every day, but I would summarize. It is the procedure how to check for complex shape webs the resistance of plate in buckling. And it's very simple. And of course, we have a lot of other ideas what procedure to use, effective thickness, effective width procedure, which is in Eurocode, or effective stress prediction. But this is for post-buckling. And I would like to show it to you maybe on this. So this is our experiment, and first point is yielding starts here. So here we have a corner, we have yielding. Then we have second point, and this is the resistance. It is here experimental resistance. Of course, we are not, we will have a prediction only. And so this is the experiment, this is the resistance. And we are able to calculate by buckling resistance. So this is buckling resistance, and there is also ultimate resistance yielding without buckling. This procedure is rather simpler, and this is what we are using. We calculate the buckling of the joint, and based on the buckling, we are trying to avoid thin plates in the connection. We are trying to help the designer to understand if the plate is thick enough to be acceptable. You know that in Eurocode there are some rules that the plate should be like flange, and there are some simplified rules, but firstly it's difficult to generalize such rules. And of course, the good engineering judgment is all the time the best. So this was the one case I was trying how we are proceed with these solutions. And second is this bolted joint. So bolted joint may be loaded in tension, may be loaded in shear. The bolts may be preloaded, they may be not preloaded. So we are treating not preloaded bolts. They are unfortunately or fortunately also preloaded, as you know. So this is this is the story. We are using a fun model, and we created the spring for tension. We have initial stiffness, and we have second stiffness. As we reach yielding in the bolt, we are going for second stiffness. We were playing with multilinear stiffness, but now we have there the linear solution. So this is the procedure, and I will show you as we validate it. Then for this, we do the test, our own test. There are hundreds of tests of bolts, but we do 15 tests just to show, just to see how it works, just to have our data, but we use for validation also another data. So these are our tests. And maybe you know with bolts, there are two behavior. One is the nut, and the second is breaking of the bolt. So here is the rupture of the thread, a rupture in the bolt. So this is behavior which is very easily simulated by advanced model. This is comparison of advanced model to experiment. And this tearing down of nut is not so easy to predict. So here is our research model. You see that it has some weaknesses, but we say this is just also based on other tests from literature. We decided that it's almost okay. And then we observed from literature already. Agerskov, my professor in Denmark, he did some study about the stiffness of the bolt because it has an influence on the connection behavior. And finally, we have also in Eurocode prediction of stiffness, and it's rather good. It's rather good. So we verify this against Eurocode. Here you see our results. So of course, based on bolt thread lengths, based on bolt lengths, you have different stiffness, force deformation diagram. So this is what is implemented in the software, behavior in tension, and we have also behavior in shear. But I'm trying to explain. I will be able to try. Then, if you have a bolt, you go to T-stop in tension. So we have now different behavior. The bolt is bends. There is really unequal stresses in the bolt. The bolt size and T-stop size is very similar. So bending is it's important for this bolt. So this is our advanced model. Here it's here is prepared in Midas software and CBFEM, and here so here, and we did also in literature beginning of this JASPAR experiments, but we do our own test once more. We did it already once more to, it's not so complicated, to have our values to be able to validate it. So here you see our test, our instrumentation, and here you see validation of solid bolt element against the test. It is global behavior. I would like to show here also local behavior. Sometimes it's relatively okay, but sometimes it's not okay. It's in experiment, sometimes it's happened that the T-stop works a bit differently. Locally, it plastify, you know, if in some place starts the plastification, maybe it not starts in another place, so it's very difficult. It is in plastic line, strain gauge, and to model the strain gauge is almost, it has some accuracy, but it has some limits. So another global deformation is okay. Now we come to verification. So we have Eurocode model for T-stop. We have plastic yielding, we have class 3, and we have breaking of the bolts. And so this is our test, and here you see the results. So this is the research FEM model, and this is the our model, the green line, and compared to component method, if the plate is thin, component method is not taking care of the membrane action, which is very significant. Here you see how much it is, because this pink is like bending, and this is our model. So we saw that we are conservative, a bit too conservative, but compared to, so we know even if we are higher compared to Eurocode prediction, T-star prediction, we are in under the we are in good numbers. So here you see the resistance based on component method. Here is resistance based on our prediction by finite element component. So this is about the bolts. And now I would like to show you 3 examples if we go to connections. So I've selected beam splices here, beam splice joint, and so here we have our calculation based on our model. And then here I am trying to show the behavior. It's not so surprising that the first row below the flange starts yielding the first and starts yielding relatively in 2/3. It's set in Eurocode that it should be in 2/3 of the by modeling bending of the plate, but it's a bit lower. And then we go through the calculation. You see the development of plastic zones, and finally we reach the red point. So this is the resistance. We go further. We go further. We go further. So here you see the comparison of the resistances. We compare the component-based method and to our. So this is verification of this. Here it's on this on another graph. Some people, they do not like it. This 45% expression, but I personally like it. So there are 2 springs in the bolt: tension and shear. And so here I have the second verification for shear, and here you see it's a bit worse, but and we are working still on it. But I think we have time till the end of the year. But tension is really perfect. Shear is still a bit question, but we have very good model, and Dr. Shabatka will show you. And now the deformation capacity. Maybe you know this particular case is very, it's relatively brittle. It's the resistance is driven by the tensile resistance of the bolts in the second bolt row. And in Eurocode, we may calculate based on this back paper, based on strain 10%. If we calculate, if we use our model based on 5% strain, we are very conservative. But we will, in our final stage, we will, for seismic design, and also for those they will be interested in this game with different material properties, we will introduce the 15%, the value which is in steel, without safety. For deformation capacity, we do not need to go for safety. For resistance, we are going for 5% strain. This is the safety. For deformation capacity, it's another question. So this is summarized here. We have support in Eurocode for seismic design. We are fully trying to fully fit to Eurocode procedures, because I think for practitioners it has a sense. They have to show the quality of prediction to authorities. Here we have, but I do not have a time, we have general loaded connection, connection loaded by here bending, but but we have also connections loaded by normal force. And I would like to show the portal frame. This was our first verification, and here you see some comparison based on size of profiles. On horizontal axis I have different A shapes, and here I have comparisons. If we go so this was welded connection. Then if we change for, sorry, this was hot rolled connection. If hot rolled profiles and connection of hot rolled profiles. If we change for plates, we come to difficulties, let's say. It's commonly known that Eurocode procedure is not, it's underestimated the resistance if the plates are thin. So we, for thin plate, these are the welded cross section. We are a bit higher. We have a bit higher. No, sorry, I'm already a bit speeding too much, and so it's on the opposite. The Eurocode procedure is not taking care of. It's a bit simplifying. It's not too far, but if we go for more advanced model, we get a bit less resistance compared what you have in Eurocode because of slender webs. Simply, it's not taking care of simply webs, and we are taking care of simply webs. So the last example I have here for joints between open and hollow section, or in these connections, it's welded connection. There is only two unknown. It's meshing and material properties. So a bit question is that we are comparing to this SIDEC material, which is fully based on experiments. So they are based not really all the time on bilinear material procedure, because it's based on experiments, and material properties is not bilinear. So, but you will see that the results are not so bad. We have also Weld model, but I will not speak about this, how to model the Weld, but Dr. Shabatka will explain you briefly how we are connecting the elements, how we are welding the elements. So here I have also global behavior. Here you see where we are. We are also plastify. It starts, the plastification start. So it is the connection between sorry, where I have it. It's open section and hollow section, rectangular hollow section. And so first starts the plastified upper flange, and then the plastification propagates through the web of the open section, and finally we reach the yielding in the web of the open section. So this is how we model, and now this verification study against the SIDEC material. Here in this case it's really very good, but we do not have enough energy to check everything. We have disconnections also in laboratory. Now next week we will do some 6 tests, so we will see if it's really so good results. So to summarize, we are reaching relatively good accuracy compared to if we are comparing this component-based finite element to component method. If not, as I was trying to show, we are going to research model and to experiments, but not to experiments or to experiments through the research model, and we are trying to compare what's the reason that our results are higher. If they are lower, we are happy. We are not going too much to we don't need to search it. We are happy that the good engineering practice is fulfilled. So verification is mathematics, validation is physics. So this is from the book, that just to summarize. And we have a bit question, because component method you may use only for very limited cases and limited loading, but component-based finite element you may use for variety connection. So component method prevents the incompetent amateurs to do mistakes, but component-based finite element method should be used by educated and good engineers. And so this is, I show you only 2 examples, and you see that we have the hierarchy very big. So at the end of the year, you will have benchmarks from this validation in the software to be able to enjoy it, to be able to use it. And we are preparing the book, which will be on our webpage, to have this study, to complete this study. So essentially, all models are wrong, but some are useful. So this is, I think, good engineering assumption. So we have, if you will be more interested, we have some reference. We publish some literature. We are, as the 6 PhD students are working on it, we publish some papers. We will have more papers about our procedure. So thank you for your attention.